we start talking about matrices, we have to first make some things clear. We have to make a few things clear. That one is, what is this session actually about? What this session is actually about? Uh, yes, it's about a matrix, but like why? Why do we need this thing? Why do we need to learn matrix? Why are you learning it? How are you learning it? And who is this? And my previous sessions are for. Uh, Let me make things clear. See, a matrix. The matrix is a really important concept in linear algebra, as well as machine learning. Matrix is the work. Uh, Matrix is a way we work with tabular data. We have a few data that we've structured in a table. Then we want to either organize the table, clean the table, do basic operation, whatever we want to do. We're doing it in this way, in with a matrix. So when in machine learning, there will be a lot of moments where you'll be using matrix to manipulate data. Let's just start. It will be clear if we start. Yep. So we're talking about matrices. Matrices, a closer look. Sorry about that. Matrices, a closer look. So before I start reading this paragraph, let me tell you what a matrix is in just one sentence. A matrix is a table that has a bunch of data. It doesn't matter what data, it has data that are structured or that are organized in rows and columns. For example, if I say I have a banana and an apple, they are both in one row, they are both in two different columns. This thing here is a matrix. See, matrix is just a form of organizing data, form of writing data. Like I have written a very good example. Imagine you have a magic box filled with numbers. Now let's organize these numbers neatly into rows and columns, just like a grid, and voila, you have created a matrix. See, we write matrix with either a first bracket or a third bracket. We write this, then we start writing our numbers or data. It doesn't matter how many rows or how many columns you have, but you have to write those data in columns and rows. That's something you have to be careful about. This will then be a matrix. Now, like I said, a matrix has a row and a column. Without rows and columns, you don't have a matrix. So since they have a row and column, they have a dimension. This is called a dimension. Matrices come in all shapes and sizes. We measure the size of a matrix by counting its rows and columns. Okay. A dimension of matrix is written as rows times columns, or R times C. Let's see this example. We have a matrix where there are two rows. First row, there's number 2 and number 3. Second row, there's number -1 and 0. We have two columns. First column, we have 2 and -1. Second column, we have 3 and 0. So we can write the dimension as 2 rows times 2 columns. This is the dimension of this matrix, RC. The dimension helps us understand what size and what shape the matrix is. So if let's say we have a 1 by 4 matrix, what does this mean? What do we know from this dimension? Like we know the matrix's size and the shape. So we can write a matrix that's similar to this one, right? Like one rows and four columns, x, y, z, a. See, this is a matrix. It has one row and it has four columns. So the dimension is 1 by 4. See, now there are, you probably guessed already that we wrote matrices. There are different shapes and sizes. There are also different types, like what kind of numbers there are, how they are arranged. On their arrangement, we can separate them into different types. For example, an identity matrix. Let's say we have a matrix, this one, a matrix A. The matrix has the data 1, 2, 3, 4. It's a completely ordinary matrix, but what if the matrix only had zeros and ones? Okay, before I actually start saying what an identity matrix is, I forgot to add a add a matrix here. That's a square matrix. See, a square matrix is where the dimensions are equal. Like if there's two rows, there will be two columns. If there are three rows, there will be three columns. If there are n rows, there will be n columns. So the matrices I wrote, like A and this one, they are both a square matrix. And every square matrix has something called a diagonal or a main diagonal. This is a diagonal. This is a main diagonal. See, this is a main diagonal. If all the numbers in this matrices except the main diagonal are 0 and the main diagonal's numbers are 1, this will be called an identity matrix. Let me write it again. This time a 3 by 3 matrix. Every single number except the main diagonal are 0. And the main diagonal consists of numbers that are only 1. So this is a 3 by 3 identity matrix. Here's a really good example that it's an n by n matrix, square matrix. This is the main diagonal. Here you can see that all the numbers aside from the main diagonal are 0. And the main diagonal consists of only one number, that's 1. This will be called an identity matrix. Now, you might have questions like why do you need to know identity matrix is, what a diagonal matrix is, what a symmetric matrix, etc, etc. See, when, like, we're not discussing it right now, but when we'll do actual maths, complicated maths, complicated maths about matrix, then we'll need these concepts. We'll need to know what an identity matrix is so we can use it in our math. You will better understand it when you actually do the math, since theory is boring, right? Now, a diagonal matrix. Like I said, every square matrix has a main diagonal. If all the numbers other than the main diagonals are 1, I mean all the numbers except the main diagonals are 0, and the main diagonals consists of only 1, then it's an identity matrix. But if the numbers are, like I said, like 1, 2, 3, now they aren't all 1. Now they will be called a diagonal matrix. So in short, what is a diagonal matrix? A diagonal matrix is a square matrix where all the elements of the main diagonal are 0. So that means your main diagonals doesn't have to be 1. It doesn't matter if it's 1 or not, but it doesn't have to be 1. As long as it's not 0 and all the other numbers are 0, this will be a diagonal matrix. So by this logic, an identity matrix is a diagonal matrix. Now let's move on to another, a symmetric matrix. Okay. Okay, before I start saying what a symmetric matrix is, there's a little more about matrices we need to know. Like, for example, there's something called a transposition. Now, what is a transposition? Or what is a transpose of a matrix? We know that a matrix has rows and columns. If there's a matrix, let's say this is ABC, this is DEF, is GHI, and we exchange the rows and columns. For example, this is the first column, we turn it into the first row. This is the second column, we turn it into the second row. Same with the last one. Now, what we did here is we exchange the rows and the columns. This process will be called transposing the matrix. Transposing the matrix, or a transpose of a matrix. If you take a matrix, you transpose it, and they come out to be the same as before, this will be called a symmetric matrix. That means there's a symmetry between the two matrices. Here, in this example, the first column, we turned it into the first row. The second column, we turned it into the second row. Third column, third row. Now, check this out. The first row and the first row here is the same. Second row and second row here is the same. Third row and third row here is the same. Turns out, even though we changed the rows and columns, the numbers didn't change. That means this is a symmetric matrix. But the matrix I wrote here, ADG, ABC, is not the same. They are not the same. That means they are not a symmetric matrix. In other words, A equals to AT. We write the transpose of a matrix as AT, T in superscript. Now, upper triangular matrix. Now, let's say we have a matrix where everything below the main diagonal is 0. This will be called an upper triangular matrix. You can if you look at it closely, every upper triangular matrix uh, makes a interesting pattern like this. It creates a triangle there. It creates a triangle with the upper half of the main diagonal. That's why it's called the upper triangular matrix. This image shows it perfectly. Like, it creates a triangle like this where everything below it is 0. This is an upper triangular matrix. And like there's exists an upper triangular matrix, there will also exist a lower triangular matrix. And you can probably already guess it. A lower triangular matrix is a matrix where everything above the lower triangle of the main diagonal is 0. So this is a lower triangular matrix. And what's a zero matrix? A zero matrix is when everything is 0. 0, 0, 0, 0. It doesn't matter what the rows are, what the columns are. If there are even rows and columns, there needs to be rows and columns to be a matrix. But if every single data, every single number, every single element is 0, this will be called a zero matrix. Okay, let me start from where I left off. We left off after discussing what matrix was. what are its a matrix's dimension, what are the types of matrices, transpose of a matrix, when it's symmetrical, when it's not, when it's upper triangular, when it's lower triangular, when it's zero, when it's an identity, etc., etc. Now let's move on to the math section. Matrix operation. See, like I said, a matrix isn't just a table. I'm sorry. A matrix isn't just a table we use for show. We're gonna actually do maths with it, and like where the best to start other than the plus, minus, and multiplication, etc., etc. So the matrix, we can do the fundamental mathematical operations with matrices. Like we can add to matrix, we can subtract to matrix, we can do matrix multiplication, or we can multiply the matrix with a separate scalar number. We'll discuss it. No, the first and the main, someone said, okay, the first and the main topic is the addition and subtraction of matrices. Let me go to OneNote to properly show you. See, we have two matrices, like one is 1 2 3 4, other is -1 -2 -3 -4. We're gonna add those two. So the it's really easy. What we're gonna do is we're gonna take the first element, find its position. The position of an element inside a matrix, we write it as we write it with subscripts, like the first row, first column. If the name of the matrix is A, by A11 we mean from the A matrix the first row and the first column. The first row and the first column is 1. So this position indicates this number. We take same positions from two matrices and we do the operation we're supposed to do, like the plus. So 1 minus 1 is 1 minus 1. The same way, this and this, they're both in the same position. So 2 minus 2. Same with here. 3 minus 3, 4 minus 4, and it turns out to be 0 0 0 0, or it's a zero matrix. So let me recap it again. What we actually do in a matrix addition is we take their positions and we add the same positions, the elements of the same positions. I accidentally forgot to allow everyone to be joined automatically. So we are adding the same elements from the same positions. So the addition of those two will be the addition of the same elements in the same position. A11 plus A prime 11, etc., etc., etc. And for subtraction, we do the same thing. Instead of writing the addition, we write subtraction. Instead of writing the addition, we write the subtraction. I made a little mistake here. Let's do an actual math. The first matrix is 1 2 3 4. The second one, I apologize for my bad handwriting, uh, like 5 6 7 8. Easy. So if we add those two matrices, 1 plus 5, 1 plus 5, 3 plus 7, 3 plus 7, 2 plus 6 and 4 plus 8. So it's 6, 8, 10 and 12. This is the addition of the matrix. We can do subtraction in the same way. There's no difference between those two. Now, the next one is a scalar multiplication. See, before we dive into what a scalar multiplication is, we have to know what a scalar is. Uh, in short, oversimplification. Like if we simplify it and say it in one word or one sentence, it's a number with no direction. With no direction. It's just a simple number like 2, like 3, like 1. That's it. It's a constant. That's it. So if we multiply it and multiply a like a b c d with a scalar or with a number, what do we get? How do we multiply it? We multiply all the elements with that scalar or with that number. This is called a scalar multiplication. The next one is a bit complicated. And that's the most complicated of the operations. It's the matrix multiplication, where we're multiplying two matrices. And the number of columns in the first matrix must be equal to the number of rows in the second matrix. The resulting matrix has the same number of rows as the first matrix and the same number of columns as the second matrix. Let's just see how it works. See, a matrix someone else is here. I apologize again. I kind of forgot to let everyone in. Okay, so we're multiplying two matrices this time, like 5, 6, 7, 8. So what we're gonna do is we're gonna take the first column and we're gonna take the first row. We're gonna multiply the first elements of both and the second elements of both. Then we're gonna add them. Let's do it. First, we're gonna take the first element, number 1. Then we're gonna take the first element here, number 5. We will multiply those two. Then we'll add the second element times the second element. See, we took the first column and the first row and then we multiplied them both. How? The first element times the first element, second element times the second element. So plus 3 times 6. Now we do the same thing to the second row. 1 times 7 plus 3 times 8. Now the next one. We take the second column and we multiply it with the first row. 2 times 5 plus 4 times 6 and 2 times 7 plus the 4 times 8. Now the result we get is like 5 plus 18, 7 plus 24, 10 plus 24, 14 plus 32, and you get the point. We'll get 4 numbers. This is called a matrix multiplication. In short, let me recap it again. We have 4 numbers. We're gonna multiply them. We take the first column from the first matrix. We take the first row from the second matrix. Then we multiply the first elements of those two. Then we add the multiplication of the second element of those two. The same thing we do for the second row. When we're doing the operation with the first row, we write it in the first row. See, there's you will notice a pattern that this is the first column, this is the first row, and the operation we did, the position is the first row and the first column. Same. When you take the second column, you have to shift it to the second column. 2 times 1 plus 3 times 2. This is a matrix multiplication. Now, a really important topic of matrices is determinants. A determinant is a single number, is a value that provides important information about the properties of matrix. Every square matrix has a determinant. The determinant is written as DA, determinant of A, or A with the 2 modular sign. Let's calculate a determinant. The matrix again is 1, 2, 3, 4. So we're gonna calculate the determinant by multiplying this and subtracting it by the multiplication of this. So 1 times 4 minus 2 times 3. Let me give another example. A, B, C, D. So what will be the determinant? We take the first element here. We multiply it with this element. We get AD. Then we subtract it. BC. We subtract it with BC. This is the determinant of this matrix. Now, see, this is pretty easy. But what if we have a 3 by 3 matrix? Then things starts to get a little complicated. See, there's a new concept when you're doing a 3 by 3 matrix is yeah. So when it's a 3 by 3 matrix and you're calculating the determinant, here's the process. First, you take the first element, you write it down, you multiply it with this. See, you extract the you okay you remove the first row and the first column since its position is the 1 and 1. Then what do you have left? It's 5, 6, 8, 9. You calculate the determinant of this and you write it here, like 5 times 9 and 8 times 6. Same thing you will do with the second element. You ignore the second column and the first row. Then what do you have left? 4, 6, 7, and 9. You calculate the determinant of this. You write the 2, multiply with 4 times 9 minus 7 times 6. And then you write a minus here. So why do you have a minus here? See, this is how it goes. I probably didn't make this explanation clear, so let me do it again. You have a 3 by 3 matrix with a bunch of numbers. You want to calculate the determinant of this. So what you're gonna do is you're gonna take the first element, multiply it with the determinant of, if you ignore the first row and first column, whatever you left, you multiply it with this. See, when you write a matrix, you write it like a third bracket or a square bracket. But when you write a determinant, you're gonna use a modular sign. Here's the modular sign. So that means this indicates the determinant of this matrix. We're gonna multiply it with 1. We're gonna do the same thing with 2. 2. Then we ignore the second column and the first row. What do you have left? 4, 6, 7, and 9. We're going to do the same thing with the third one. We ignore this and this. What do you have left? 3 times 4, 5, and 7, 8. Now, what are we supposed to do with these 3 values? Are we supposed to add them, subtract them, multiply them, divide them? What? So it goes like this. If you have a 3 by 3 matrix, whatever the numbers are, x, y, z, here's how it goes. The first row and first column is plus sign. You go one step down, it becomes a minus. You go one step down, it becomes a plus again. Same thing here. It becomes a minus, it becomes a plus. This is a really easy way to understand when we're supposed to use the negative sign and when we're supposed to use the positive sign. Here, we did calculations for the first one since we know that it always starts with plus plus, so we write a plus here. Then the second one, after plus comes a negative and a minus, so we write a minus here. After that it comes a plus again, so we write a plus here. Now let's finish calculating this matrix or this determinant. 1 times 5 times 9 and 8 times 6. 5 9 minus 8 6 minus 2 into 4 times 9 minus 7 times 6 and then the final one 3 times 4 times 8 minus 7 times 5. What do we have left? 45. 3 times minus 3, we get minus 3 plus 12 minus 9, we get 0. So the determinant of this matrix is 0. That's how we calculate the determinant of a matrix. And a lot of you arrived a little late, so I already discussed what a matrix was, how it works, why we need it, etc., etc., the types of matrices. So if something's is remains confusing for you, you can watch the recorded session which I'll upload in my YouTube channel. And like I said before, a lot of people probably don't know I have a fever, so I'm feeling a little under the weather today. I probably won't be able to continue it for long. Now, what do you have left? How much are we gonna cover? Application of matrix, linear systems with matrix, row echelon and reduced row echelon, matrix inversion, advanced concepts and techniques, determinants. Should we continue? Yeah, I think we should stop it here. Yep, let's do one last let's do one last concept, that is the matrix inversion, and we'll learn about the next row echelon and reduced row echelon form of matrices in the next session, since it will take way too long for me to actually cover everything. Since row echelon and reduced row echelon takes a lot of time to practice, to do, to explain, and solving linear systems will take an hour on its own to actually explain how everything works. And the applications, we'll discuss it. So for today, since I'm feeling a little under the weather, will the last topic will be the matrix inversion. Okay, what is an inverse of a matrix? What does inverse of a matrix mean? Let's say we have a matrix 1 2 3 4 A. We want to invert the matrix. So in order to invert the matrix, you do the following. You calculate the determinant of that matrix. You divide it by 1, or you divide the determinant with 1. Then you calculate the adjoint of the A matrix. See, we know how to calculate the determinants. We don't know how to calculate the adjoints of A. Is it adjoints? Whatever, ADJ. So how do we do it? So it's really easy if you're doing a 2 by 2 matrix. We just okay. Let's do it with a 3 by 3 matrix. It will be easier to start with the hard one. The matrix is 1 2 3 4 5 6 7 8 9, the easiest one. We're gonna calculate that. At first we're gonna calculate the determinant. What will be the determinant of this? Like 5 9 is okay, whatever. I don't know if I can continue anymore, but we're gonna calculate the determinant from this matrix. Then what we're gonna do is we're gonna find out the adjoints of each elements. We're gonna find the cofactor of each element. A cofactor is the value like this one. This operation that we did, this is called a cofactor. We're gonna do this operation for every single element this matrix has. For the first one, 5 9 minus a6, 35 minus 48. Oh, sorry, 45 minus 48. So this will be minus 3. For the second element, we're gonna do what we did here. The same thing. It's the same. So the second element will be 4 times 9, 36, minus 6 times 7, 42. So it will be minus 6. No, it won't be minus 6. Since it starts from plus, then it goes to minus, then it goes to plus. So it will be minus minus 6 or a plus 6. Same way we're gonna calculate every single element of that matrix. This, the final version of the matrix, is the inverse of the original matrix. This is called the inversion of a matrix. Let me say it again. If you have a 3 by 3 matrix, a lot of people are joining when it's almost over. So if we have a 3 by 3 matrix and we want to calculate the inverse of like A, we take the determinant of A, then we write 1 by determinant of A, then we calculate the adjoint of A, which is the cofactor of every single element in the original matrix, and the cofactor is like if we have A, B, C, D, E, F, G, H, I, we do this. We calculate the determinant of this. E times whatever this is, I wrote I minus FH, then we multiplied it with A. We write it here, here, here. For every single element, we write it there. And whatever you get, we divide it with the determinant of the original matrix. The result will be a inverse of the original matrix. This is called the inversion of a matrix. There's an interesting operation where if you multiply a, a matrix with its inverse, we get an identity matrix. You can try it out. Write a matrix on your own, calculate the inverse, then multiply them, do a matrix multiplication. You will get an identity matrix. I don't know if you remember or not. An identity matrix was where the in a square matrix where only uh, everything other than the main diagonal was 0 and the main diagonal consisted of only one number, that is 1. So this was the inversion of a matrix. I had a lot of other things in plan. I was supposed to talk about what a row echelon and a reduced row echelon forms of matrices are. But in order to talk about those, we're gonna have to talk about how we do row operations, column operations, in order to calculate the row echelon and reduced row echelon forms. We're supposed to solve linear system. We're supposed to have a lot of problems. Then we're supposed to convert them into a matrix. Then we're supposed to solve it to get a meaningful answer. Then we're supposed to talk about the applications, how matrices are used, how linear algebra is used in machine learning in general. And my session is meant for like absolute beginners who are either starting with math or know a little but wants to dive deep for them. But I apologize since I can't continue today. My fever took the better of me. But thanks everyone for coming. A lot of you arrived late. You guys can watch the recording session of this session. But if does anyone have any questions? No, I guess. Then thank you for coming. I'll end this session here.